All right, so some applications, some examples of some kind of problems that we would solve dealing with Extrema. These Extrema problems they make me think of like working on a car. There's a lot of stuff involved and your hands get really dirty and there's a lot of things that you have to keep track of. Not as clean and tidy as a lot of the math that we end up doing. Gradients are kind of clean and tidy. Extrema, kind of messy. That's the way I see it. All right, so our first example, we have this paraboloid. Z equals x squared plus y squared. We want to find, we have a point. The point is 550. So we have this point on the xy plane. We want the minimum distance from the point to the surface. So if we were to draw a quick sketch here of what we're looking at, we have this nice paraboloid. And we have the point 550 here. And we want to minimize this distance from the point to the surface. Well, to work this problem, what are we going to need to do? What's our function that we're minimizing? A distance. So we need to write some kind of expression for our distance. So distance between 2 points in space, I gave you a hint, square root of just some point x. I'm just going to say x minus x0 squared plus y minus y0 squared plus z minus z0 squared. So on the paraboloid, so on our surface, we're just going to say x equals x, y equals y, and z equals x squared plus y squared. So now, if I substitute these in, I have a function of 2 variables rather than a function of 3 variables. Because right now, the way I wrote it here, this is a function of 3 variables. On my surface, I can change it to a function of 2 variables. So the distance on the surface, distance is going to be square root of x minus 5 squared. That's our point that we're interested in, plus y minus 5 squared. Plus, and our point z, we're going to say x squared minus y squared minus 0 squared.
Why is it minus squared?
Sorry. Because I made a mistake. So there's our function, there's our distance function. And we want to minimize this. So we've done these problems like this several times. What are we going to do to simplify our work? Essentially minimize d squared, right? Just minimize what's under the radical. So we're going to minimize this radicand, x minus 5 squared plus y minus 5 squared plus x squared plus y squared. Got the sign right this time. Squared. So we're gonna apply our methods for minimizing this function. So this is a function we want to minimize. So we're going to find our first partials with respect to x, partial with respect to x, partial with respect to y, and see where those are 0 simultaneously. So the partial of d, whoops, I forgot my square here. The partial of d with respect to x, d sub x, is going to be what? X times x squared plus y squared. Looks good to me. Everybody agree? And we have a similar derivative for y. D sub y is going to be 2 times y minus 5. We have kind of a symmetrical situation here. Plus 4y times x squared plus y squared. And we want both of those equal to 0. So let me see if I can remember how to do this. So I want to do this, and do this, and I want to do that. Oh, it's in the same place, so then can I do this? No. I want to just be able to undo that. So I should be able to, no. I should be able to select that. Well, I'll have to practice with that more. All right, so, because I want to drag that up to the top. And I know I can do it, I just can't remember how to do it now. It won't let me select it again. So there's some step I'm missing.
There, look at the top first and then copy it and then paste it.
Yeah.
Paste it in.
I don't know.
It pastes, what it's doing is pasting it in the same position on this page.
What's that magnet thing?
This one? Yeah, I tried that. Because it won't let me select.
What's that thing that's placed above the arrow on the left side? Above the cursor on the left side?
Yeah, I can't.
What's that thing that's selected out?
Yeah.
The thing that's pressed down?
Yeah, I can't unselect that. No, it's lesson mode. Pen mode. All right, I thought it was going to be fancy here, but it's not working.
Copy on this page while you can still see it. So you don't have to.
Okay. All right. Yeah, it won't let me select. Oh, there we go. Yay! Thank you. Now, no. Okay, got the select part. Now I have to, where is my?
I think it's right the cursor.
Probably.
It should give me a. That'll rotate it. Hey, I can't move it. That'll let me stretch it.
Oh, right here.
There. There.
Oh, but I think. Oh. All right, we figured it out. Okay. There's. Now that our class is almost over, there are our partial derivatives, and we want each of these equal to 0. That's actually the first time I've ever done it. I've practiced it. That's the first time I've done it in class, so I'm excited. I took a whole class on using interactive whiteboard technology. And most of the stuff I already knew, but there were a few things that I learned, and that was one of them. And I thought it would be good in this class so I don't have to rewrite these long equations. So there's what we want. If we simplify this, if we simplify our expressions, this is going to simplify. I'm going to call this equation 1 and this equation 2. If we simplify these, this is going to simplify to, if I expand this out, this is going to tell me that x plus 2x to the third plus 2xy squared equals 5. I'm going to simplify this, and I'm not going to go through all the steps. So equation 1 gives us this, and equation 2 is going to simplify to y plus 2y to the third plus 2x squared y also equals 5. So I have these two equations. So I have these simultaneous equations that I need to solve, and they have these x squareds and these y to the thirds. And we need to simplify this. Anybody have an idea of what we would do here? We want to try to use elimination here. So what I'm going to do is we're going to multiply the first multiply 1 by y, and multiply 2 by x. So I get xy plus 2x to the third y plus 2xy to the third equals 5y. And when I multiply the second one by x, I get xy plus 2xy to the third plus 2x to the third y equals 5x. So we're trying to eliminate one of these terms. Now we're going to subtract. So I'm going to subtract, and I end up with 5y minus 5x equals 0. So this tells us that y equals x. What's that? Minus 5, yeah, that should be 5x. 5y minus 5y does equal 0.
Yeah.
But yeah, it should be 5y minus 5x equals 0. So y equals x. Now I'm going to substitute this back into equation 1. Substitute into 1. And we get, substitute into that first equation, and we get x squared plus 2x to the third plus 2x to the third equals 5. This is going into equation 1. Oh, sorry. This should not be an x squared. So I'm substituting y equals x into this equation. Thank you. So we get this equation, and now we can solve this one. We can solve this one for x. I'm going to combine these terms and factor. So I get x times 4x squared plus 1 equals 5. Anybody see what the solution here is going to be? X equals 1. So we can say by inspection x equals 1. And now we're just going to substitute x equals 1 into our original, into equation 1. So we're going to substitute into equation 1, and we get what? Oh yes. So we had y equals x, so y equals 1. So y equals x. We could substitute and get it also, but we know that y equals x. So y equals 1 also. And z equals x squared plus y squared. So z equals 2. And then we can find our distance. Our distance that we were looking for
So
was,
that gave us the point where that is minimum?
right, that's the point where our distance is minimized.
How do we,
The point on the surface?
Yes, the point on the surface.
how do we know that's the minimum or maximum?
We could run our second partial test to see that it's a minimum. If
Since it's a problem is symmetrical, if the numbers are negative, that would mean it's going to be opposite positive.
right, and that's exact. So I was going to say what Mehmed just said. If we substituted x equals 1 into our equation, we would get a solution y equals plus or minus 1. And if y equals minus 1, we're in the opposite quadrant, or the opposite octant, I guess, a different octant than our original point. So we could see by knowing where our point was and what the graph of the surface, that point couldn't be a minimum, that would have to be a larger distance. Does that make sense? Okay. All right, so I'm just substituting back into our radical for distance. We get 1 minus 5 squared plus 1 minus 5 squared again, because x and y both equal 1, plus 0 minus 2, or sorry, 2 minus 0 squared. I guess it doesn't really matter. And we see that our minimum distance is 6 units. So on the surface, the minimum distance, we have x equals 1, y equals 1, z equals 2, and our minimum distance is 6. So one type of application problem. Questions on that one? Okay, let's look at another one.
Basically, our multiple phase is like 13.8.
That's a good portion of it. We still get to talk about Lagrange multipliers. Those problems aren't long, but another example. We want 3 positive integers. Such that the sum is 32, and x, y squared, z is a maximum. And we want our positive integers to be x, y, and z. So we want 3 positive integers, x, y, and z, such that the sum is 32 and x, y squared, z is a maximum. So this particular problem, we have a function that we're trying to maximize, but we also have a constraint. Our constraint is the sum has to be 32. So we have that x plus y plus z equals 32. So that's our constraint. We're constrained by that condition. And our function, let's say that f of xyz is xy squared z. So that's what we're trying to maximize. We want to maximize f subject to this constraint. Lagrange multipliers that we'll talk about on Friday all is a procedure for doing these kinds of problems where we have a function and a constraint. We're going to do this one in a slightly different way today, because just so we see how we would apply the tools that we already know to do this kind of problem. So what I'm going to do is use the constraint to eliminate one of these variables. So this constraint, we can think of this constraint as a surface. So x plus y plus z, what kind of surface would that be? A plane. So we have some f of x, y, z. If we think of this function being a constant, we have a plane cutting through that level surface. So we have a plane cutting through this surface, so we're maximizing this. On this surface, we're maximizing this quantity that's on the intersection of that with the plane. So we're going to use the constraint to eliminate one of the variables. So on the constraint, we have z equals 32 minus x minus y. And I'm going to substitute that into my function to eliminate z in my function. So f is going to be xy squared times z, 32 minus x minus y. And if I distribute here, I end up with this being 32 xy squared minus x squared y squared minus xy to the third. So this is what we're trying to maximize. We have a two-variable function. We want to maximize this, and we're going to use the tools that we know already to maximize it. So our partial derivative with respect to x, f sub x, is going to be what? Minus y cubed. And we want that equal to 0. So I'm going to make this, we're going to try to make this easy on ourselves. We'll factor out a y squared. So we get y squared times 32 minus 2x minus y equals 0. Now we're going to ignore the solution here that y equals 0. If y equals 0, our function is 0. So we're going to ignore the solution y equals 0. And we're going to say that we want 32 minus 2x minus y equals 0. We will also do it for f of y. So I just want to get this, first. So I'm going to solve this for y. We get y equals 32 minus 2x. Now we'll do our partial with respect to y. Partial with respect to y here is going to be what? Okay, perfect. And that we want that equal to 0 also. So we'll make our lives easier here. We're going to factor out a y. Y times 64x, I'm sorry. We could factor out an x also, so we could, let's see, so we get 64xy times 64 minus 2x minus, oh, I didn't bring out, I didn't, don't want that. Minus 3y. And that equals 0. And again, we're going to ignore x and y equals 0 because that's just going to give us a 0 for our function up here. So we have 64 minus 2x minus 3y equals 0. from our partial with respect to x, we know that y equals 32 minus 2x. So I'm going to substitute that in here for y. So I get 64 minus 2x minus 3 times 32 minus 2x. And that has to equal 0. And I get, when I simplify this, 64 minus 2x minus 96, sorry, I was being hopeful, minus 96 plus 6x, and that equals 0. And this simplifies to, let's see, we get 4x minus 64 minus 96 is, what is it? 32 equals 0. And from this I get x equals 8. X equals 8. I can substitute it into our expression here for y. So y equals 16. I substitute x in here. And finally I get z equals, and I'm going to use this expression for z, plug in our x and our y, and I get z equals 8 also. So x equals 8, y equals 16, and z equals 8. That's going to maximize. I used this one from the constraint. That's going to maximize this function such that their sum is 32. So this is one way we can maximize a function subject to a constraint. We use a constraint to eliminate one of the variables. Questions on that one? All right. This next little piece that I want to talk about is not something that you're going to have to do homework having to do with. It's not something I'm going to put on a test. It's just kind of an extension that I wanted to talk about, because we've gotten to a point where we have all the tools where we know how this works now. So I just find it kind of interesting. You could, for your own edification, right? So least squares line. So we use least squares, and your calculator does it really well. So we have a set of data points. So we have these points, x1, y1, x2, y2, etc., etc. So we have some collection of data. And we want to fit a line to this data. So we want to fit this with y equals f of x, where our function is linear. So if I draw just a quick sketch here of what we're talking about. So let's say I have a point here, and a point here, and a point here, and a point here. And we want to fit some line to that data. So we're going to say something like this. So one way that we can fit our line, make a good fit for the line, is to minimize the squares of these distances. The sum of the squares of these distances. So this is d1, d2, d3, d4. And we minimize the squares for the same reason we minimize the square in that problem that we did with paraboloid. Because we minimize the square, we don't have to deal with that radical. So we're minimizing the squares of these distances. So we're summing up the squares of these distances, and we're minimizing that sum. So that's one way to fit a line to this data, is minimize the sum of the squares of those distances. So we're minimizing the sum of f of x sub I minus y sub I squared. So our function, we have our function value on our line, and we have our y value at our points. We want to minimize that distance. We're trying to find that function that minimizes that distance. And for this particular model, we want a line, so we're saying that f of x is ax plus b. Some line with some slope and some intercept. So the sum is a function of a and b. So we have this sum that's a function of two variables, a and b. So we have a two variable function, and we want to minimize that function with respect to a and b. We want to find a and b such that this function is minimized. So if you think about the process, our function is not just a nice function where we can say x squared plus 3y plus something else. We have this sum, so we're summing all of these things. So our function is a sum. Well, we have the methods now. We have all of the techniques to minimize this function of two variables. We take the first partials of s with respect to a and with respect to b, set them to 0, run the second partial test to ensure that we have a minimum. Now what this gives us, I'm not going to go through the process because it's extremely involved, but it's the tools that we've been using. We get that, I just want you guys to see this, a, when we minimize that function with respect to a and b by taking our first partial, setting them equal to 0, ensuring we have a minimum with the second partials test. A is n times the sum I equals 1 to n, x sub I, y sub I, minus sum I equals 1 to n, x sub I, times the sum I equals 1 to n, y sub I, divided by n, sum of I equals 1 to n of x sub I squared, minus the entire sum squared. So that's what we get for A. And B, a little less complicated. B is 1 over n times the sum I equals 1 to n of y sub I minus a sum I equals 1 to n x sub I. And y equals ax plus b. And that's our least squares line for our data points. So imagine having to calculate this by hand. So the people that when least squares line was originally developed to fit data to a line, you had to calculate these sums for all of your data points. But we proved that this is our least squares line by using the first partials, setting the first partials equal to 0, ensuring we have a minimum with the second partials test. So we have developed at this point we've developed the tools to do this thing that you learn to do in like Algebra 1 with your calculator. We have the tools to, and we can understand where that procedure comes from. The linear regression, exactly. So this is like doing linear regression in your calculator. Yes. You are never going to be tested, not by me anyway. I can't guarantee in the future, but I just found it. I think it's an interesting application of what we've been learning. That that we've got the tools now to understand where least squares regression comes from. All right, homework. There you go.